Anyway, so the simplest thing to do is what's called one versus all approach. You build, if you have K classes, you build K classifiers, right? Each of them classifying one versus the others. So I built one classifier for the red circles, one classifier for the green circles, one classifier for the yellow circles, right? So I end up having, for this particular case, so three models, right? And then when I'm actually doing the classification, I would give an example. I would run my example through all three models, and I see which one of them lights up, which one of them say yes. Hopefully only one would say yes, in which case you just pick that one. If more than one say yes, you need a way to break ties. And again, there's no standard way of doing it. You can try and look at past statistics on that on the models and see which one has a lower false positive rate or false negative rate or error rate. But essentially, for most of your sklearn models, at least for the SVMs, it's doing one versus all. All right. There's an alternative, which is I'm not sure if there's an official name for it. It could be one versus one. In which case, so this one you will build three models. If you have K classes, right? You're going to build K models. The other one, this is one versus one, I think. This one you're going to build a model for every pair, every pairing. So you're going to build K times K minus 1 divided by 2 models. Okay, and then again, you would, during classification, you just run it through the K times K minus 1 over 2 models and see which one lights up. And you can figure out a way to resolve any ties or anything, any issues like that. You can kind of weight them too. All right. But again, so these are, again, you will see these terms in sklearn documentation as well when they talk about multi-class for, say, SVMs and stuff like that. And so this is, again, something that's good to know. All right. Okay, questions on multi-class. Okay, good. Okay, actually, before we go on, right, since we're talking about, let's see, for the single perceptron, there is I have the link here on the website. You can go to it. This is a demo that you could play with if you want. You can choose you can start clicking points. Right now it's blue, so I can click blue points, blue points, blue points, blue points, blue points, blue points, and red points, red points, red points, red points. And every time I click, it's going to do gradient descent to try and tune the weights of that hyperplane, the W vector of the hyperplane, in order to try and separate the points. It's not doing very well right now because it's just doing one iteration of gradient descent. So if I keep doing train, it starts getting it right. One more time. And then it sort of gets it, okay? So this is, again, this is a visualization of how the gradient descent work for a single perceptron, right? Oh, and this is the learning rate parameter that we talked about, right? Okay, so you can play with this. You can also play with multi-layer. This is the This is the TensorFlow playground, and those of you from Peter's class will have seen this. I'm not really going to go through this, but here you can set up your number of hidden neurons, and you can give it that circle data set that we saw, and you can see how it trains. So with one layer, for example, like the perceptron, we'll never get it, but with two hidden layers, it actually starts to get it. All right, it starts to the colors denote the decision boundaries. It doesn't show up very well. So the colors denote that the model is going to classify everything here as blue, everything here as orange, right? So it's a little bit better than just a straight line. But it got it, all right? So this was after many epochs of training. Okay, but of course, if you set it to just a single neuron, tough luck. Wait, how do I reset the data? Oh, here. I think. So it's just a hyperplane that's trying to separate the data, and we know it's tough, but it's still fun to watch. So this can be a pretty addictive website. Actually, I've spent some time on it. Okay, but kind of fun. Fun to watch, right? Okay. So that was that. Next thing that I want to quickly talk about, and is that look what we're doing here, right? Things are starting to get interesting, because it's like before we're using a single model to do my prediction or classification, but now I'm starting to use more than one model. I have 3 models here. I have basically n squared models here. So then you can kind of think of sort of generalizing this into what's often now called ensemble methods. Anybody heard of ensembles? What does ensemble mean? I've heard of string ensembles, music ensembles, right? So it's like a group of people playing music together, right? So it's a group of models, right? A group of models. So that's why I call ensemble methods. I have an ensemble of models doing the prediction, right? And there's sort of 2 big classes of techniques here. One is called bagging, and I think bagging is actually short for bootstrap aggregation, I believe. I know, weird terms. Okay, this is the easier one, right? And the most famous of this is what's called random forest. Now, if you thought one decision tree was good, what about 2 decision trees? What about 3? What about 4 decision trees? That's the idea. Okay, so random forest, what it does is this. I'm going to take random subsets from training data, and this is sampling with replacement. Okay, sampling with replacement. All right. So I take random subset, and suppose if I take 100 random subsets from the training data without sampling without replacement, and I build 100 decision trees from each of the subset of training data. Okay, and then when I want to do my classification, I run my example through the 100 decision trees, and I can take a simple vote. I mean, if it's classification, if it's regression, I can take some kind of average as well. All right. Turns out that improves the accuracy. Okay, so so this is often thought of as a way to improve that you can have an ensemble of weak learners, also not very powerful models, but somehow an ensemble of not very powerful models can become pretty powerful after you put them together. Okay, it's actually a nice idea, right? I'm not sure if it exactly works with humans. So.
You have to be trained.
Will a group of not so intelligent, say not so great chess players beat a world-class chess player? It's a good question.
An ensemble of chess players could probably beat the world's chess player.
Okay.
If they do that, the world is sufficient. I mean, if you have an ensemble of highly specialized chess players, like one's really good at defensive stuff, and other people are good at those things, then maybe you have to do it.
Yeah.
If they're just random people, then
This doesn't help much, but one of my friends is like a chess grandmaster, and I did see him beat a group of people working together, while he was blindfolded.
Wow. Anyway, cool. So you will see random forest being mentioned somewhere. Yeah, random forest was really popular maybe 10 years ago. It has since been superseded by the next technique, which is called boosting, and this is the last thing that we'll talk about that's in this whole data mining, machine learning area. The notion of boosting. Okay. So in bagging, we just pick the 100 random subsets, right? And we can basically do all 100 things at once. We can build all 100 models at once, almost simultaneously, right? Boosting is a bit different. Instead of doing it simultaneously, I'm going to do it sequentially. And what's the reason for that? I'm going to build a model sequentially. So build a model sequentially. And I'm doing it because I'm going to build my first model. I'm going to do M1, right? Then I'm going to see which examples are not well classified, which examples are wrongly classified. Right? And I'm going to make sure that M2 specializes on getting those wrong examples right. Okay? So my ensemble now consists of M1 and M2. So whatever M1 gets wrong, hopefully M2 will get it right. Right? And I keep doing the same. M3 will be whatever that these guys before me got wrong. Yes?
Sorry, is M2 and M3 a completely different type of model, or?
But usually the same kind.
Same model with different
again,
parameters.
think decision trees.
Okay.
Right, yeah, good point. So, yeah, for some reason people like to apply ensemble methods to decision trees because somehow they think decision trees are sort of weak models, if you will. But the other thing is because decision trees are relatively easy to train. That is the other thing, right? So yeah, so think decision trees. Good question. Thanks for asking that. Actually, think decision trees, right? But you could apply to SVMs. You could apply to SVMs, right? Yeah, and then so if you build 100 models, you'll be building 100 models in this way, always trying to give, always trying to emphasize examples that the previous models got wrong. All right. So this is the notion of boosting. All right. And in a very similar way, along this idea, you have what's called sort of gradient boosting, right? Again, it's a similar idea, but again, if you think of, say, regression trees instead of decision trees that are used to predict a continuous variable, that would be easier to understand. You are finding what, say, your model. Let's use M again. Oops. I mean, your model one will predict something, and whatever that model one does not predict well, or you will find what's called the residual. Let me introduce that term, residual. It's the true y minus the predicted y, which is m1x. That's called your residual. All right. So you would then create a model M2 to predict the residual, and your model, your combined model at that point in time, let me use capital M, is going to be equals to M1x plus M2x. All right, and then for M3 is going to try to predict the residual from the combined model of the previous step. All right, I should put in a time index here, but yeah, let's do that. Let's call this M2. So it's trying to predict this one and 1x, where well, capital R, I'm not distinguishing my capital to my small. M1x is just this guy. Okay, so this can be shown to look a bit like a gradient. So you're sort of it's like you're trying to do boosting, but like doing gradient descent as well. Again, I'm not going to go into the math for this. Okay. So this is gradient boosting, and again, this has been really, in recent years, this has won quite a few Kaggle competitions. There's a package called XGBoost, which is supposed to be a really efficient package for this. sklearn also has a package for this called Gradient Boosted Trees. Gradient Boosted Trees, which is essentially doing this. All right. Okay. Very quickly. Never mind. Hang on, let me just get rid of these guys. Bunch of nice demos as well. Oh, there's a. Let's okay. Well, let's take a look at this one. So this is random forest ensemble of 100 trees, and let's see what I'm supposed to do with this one. Let's see. I did this earlier. Add a red point. Let's see. Add a red point. Okay. Add a green point. Ooh. So it started to learn. Red point. So these decision boundaries, you kind of see these square shaped stuff. That's what's produced by the splitting of the decision trees. But now you're combining the splits from 100 different trees, kind of like superimpose on each other. That's what this is kind of doing. So again, it's kind of cute to play with. There's some nice visualization here. We're not gonna go through everything, but just show you one. Oh yeah, this one is so nice. This one has a kind of a visualization for decision tree as well. Ooh. Oh crap. Okay, sorry. This doesn't work on this computer. All right, you guys gotta try this on your own. Somehow I think my Chrome version or something might not be. WebGL is not supported by my browser. All right, I will install something. Okay. Okay, so any questions on anything? So that's all we're gonna do for the machine learning stuff. Gradient boosting is kind of cool. But yeah, those who are in Peter's class, right? If you look at this, this is very similar to the residual blocks in the ResNets that Peter was talking about. If you look at the structure, it's pretty much it's actually doing that. It's trying to predict the residual. So kind of cute. Questions? Otherwise, next class we're going to do probability and statistics, and yeah, we'll see how that goes. Okay, that's it for today then. Thank you.